Hey guys, Mr. Jenkins here with our last lesson of Chapter 7 that we're going to be covering. So we will have a test in a few days, and Math XL's due soon. So first four lessons of Chapter 5, all about kind of exponent laws and stuff like that. Switches gears a little bit today, talking about rational exponents and radicals. Basically, we want to be able to do two things after this lesson is over. One part of the learning target is we want to be able to rewrite expressions involving radicals and rational exponents. The other part that we are adding now is that we also want to be able to simplify irrational square roots. So those will be added on at the end. All right, so let's go ahead and get right to it. So this key concept says the nth root of a is a real number, m is an integer, and m over n is in lowest terms. Then a to the 1 over n equals the nth root of a, and a to the m over n equals the nth root of a to the m, which can be written either this way or this way. So the exponent can be either inside or outside of the radical. A simple way that I can remember that is, dealing with these fraction exponents. I think of the numerator of my fraction, which we just referred to as m, as the exponent or the power, and the denominator part of it as the root, or there was that vocab word up there. Root can also be called an index. So a root or the index. All right, so that's going to deal with the first part of our learning target. Okay, so let's go ahead and look at finding some roots, kind of using our calculator. All of these are rational numbers, so when we simplify these roots, we should get whole number answers. All right, so one way to simplify these is just to know how to use your calculator and type in the cube root of 125. So on this TI-84, I can go to math, and the cube root is the fourth option down. There you see my cube root radical, and then whatever I want to find the cube root of goes under the radical, and so we can see the cube root of 125 is 5 per our calculator. And the reason that that is true is because what we're saying there is that 5 to the third power equals 125. So that would be another way to simplify one of these roots, is to just guess and check. What number to the third power equals 125? Okay, so that would be one approach, or we could use also what we know about rational exponents, and we could, if we're better at typing in exponents on our calculator, we could type in the fourth root of 16, looking at the next example, as 16 to the power of 1/4, because those are equivalent. Okay, so I could also use my calculator on that. Type in 16, which is my base, caret key, and then 1/4. Depending on what kind of calculator you have, you may have to put the 1/4 in parentheses. With this calculator, I do not. You can see the 1/4 is all part of the exponent. Now I hit equals, and so I can see that 16 to the power of 1/4, or the fourth root of 16, is equal to 2. And again, why is that true? That's true because 2 to the fourth power is equal to 16. All right, the rest of these, C through F, are worked out on the notes, and so you can check there for what C is, the fifth root of 32, all the way through F. Okay, one note about F is the second root of 36 is usually not written the way it is there. It would normally be written with no number for the index. So second root of 36, we usually call the square root of 36, and it's usually written that way. All right, moving on to example 2. Now we're going to convert to radical form from exponent form. Okay, so looking at A, I know A is what goes under the radical. Now I need to figure out where do the 5 and the 6 go. So remember what we said, the numerator of your fraction exponent acts like the power or the exponent, and the denominator acts like the index or the root. So the 6 goes here, the 6th root of, and then the 5 goes here, the 6th root of A to the 5th. You can write it that way, or what might be easier, actually I prefer to write it this way, the 6th root of A and then to the 5th power. So that 5 can be outside or under the radical, that 5 exponent. Okay, do a couple more, and then you can check the notes for the rest. Okay, looking at example B, some people would get this wrong and they would think the 12a goes under the radical, but actually the exponent of 12 is 1. Okay, so the 12 actually goes outside the radical here. So we're thinking it's 12 times the radical, some radical of a. Okay, now we figure out where the 3 and the 2 go. So the 3 is my root, the 2 is my power. So I can read this answer as 12 times the cube root of a squared. 12 cube roots of a squared. Sometimes it looks a little bit confusing when you're doing this on paper. So it kind of can look like 12 cubed times the square root of a. So just to avoid that, you can put a little multiplication symbol in between the 12 and your radical. Notice example C looks a little bit different in that 64a is in parentheses, meaning that it's all going to go under the radical. The 64a is all under the radical here. Okay, so kind of like that. And then the 5 is my index or my root. The 4 is my exponent or my power. Okay, now you do want to be careful here with where the 4 goes. If you put the 4 under the radical, you would need to use parentheses around the 64a. So if you wanted to rewrite this, the 5th root of 64a to the 4th would be wrong. Whereas to make it correct, you do the 5th root of 64a grouped in parentheses to the 4th power. So that's why I say sometimes it's easiest just to put that exponent outside the radical. Okay. All right. So then D, E, and F are all worked out on the notes. F is a little bit tricky because we have to multiply same bases first. All right, so moving on to example 3. Now we're going back the other way. We're going to write each one, we're going to convert from radical form to exponent form. Okay, so this should be pretty easy based on our last example. So looking at A, we want to rewrite that as B to some power. So the 3 is the numerator, the 5 is the denominator. So my exponent is 3 over 5. Now again, when you're writing this on paper, you just want to be clear that 3/5 is an exponent. So we're not used to writing exponents as fractions necessarily. I like to use the kind of side-by-side fraction when I'm writing them as exponents. Okay. All right, looking at example B. So again, this one could be a little bit tricky, but the 5, remember, only goes with the D part of the factor, right? So we could read this as the cube root of 27 to the 1st power times D to the 5th power. So that will affect how everything looks. So my exponent for 27 is going to be 1 over 3. And my exponent for D is going to be 5 over 3. Okay, so all we're doing here is writing in exponent form, so we'd be done there. If our directions were to simplify, then we would want to know, what is 27 to the 1/3 power or the cube root of 27. So if I were just simplifying, I would want to figure out that 27 to the power of 1/3 is 3. So fully simplified, that would be 3d to the 5/3. Okay, so kind of pay attention to the directions there. All right, and then I'm going to skip C because it's a lot like B, and let's maybe look at how F is a little bit different. Okay, so with example F, the 5 exponent goes with the 4 and the y, right? So this could also be written as radical 4 to the 5th, y to the 5th, right? So it's good to understand how those parentheses change what we see. Okay. Another tricky thing here is, what is my index? Okay, that could trip you up here because the square root or the second root, you won't always see a 2 there, right? So that's understood to be there. Okay. Now that we have all that, we can write this as 4y grouped in parentheses to the power of 5/2. Or if you wanted to write it a different way, that'd be 4 to the power of 5/2, which could be simplified, times y to the power of 5/2. So again, if we were fully simplifying, we'd want to know what is 4 to the power of 5/2. And again, using our calculator, we could see that that's 32. Okay, but all we're doing is writing in exponent form. So you can check the filled out notes for the solutions to C, D, and E, but I'm going to go ahead and skip ahead and do our last little bit. So there's a word problem on my original notes. We're just going to skip that for today and look at the second part of our learning target, which is how to simplify irrational numbers that are square roots. Okay. So first of all, what's it mean for a number to be irrational? Well, one irrational number that's very famous is pi. That's a number that never terminates, never repeats, and neither do any of these, right? So if I use my calculator and I type, say, the square root of 12, I'm going to get a number like that. Now, it does come to an end on my calculator because my calculator just runs out of space. But anytime you do a radical of a number and get a number that looks like that, that's an irrational number. So that 3.464 ... number never terminates, never repeats, goes on forever without a pattern. Okay. So anyways, we have our own special way to kind of reduce these or simplify these. Okay. So what we want to think about here are basically, our first several perfect squares. Okay, so I'm going to list some of those out. So 1 squared is 1, so that tells me that 1 is equal to the square root of 1. Now, we don't usually use this because 1 goes into everything, so I ignore this one. Then I could say 2 is equal to the square root of 4. 3 to the square root of 9. 4 is equivalent to the square root of 16. And I could just keep going on forever, but I'm going to just list out the first several perfect squares, and then I'll tell you how to use them to help simplify some of these radicals. 7 is equal to the square root of 49, and I'm about out of space there, so I'll stop there. I could keep going. 8 equal to the square root of 64, and so on and so forth. Okay. So if I'm going to simplify any of these non-perfect, square roots of non-perfect squares, what I want to do is basically write what's under the radical as a product of a perfect square, times whatever is left. Okay. So looking at example A, then the square root of 12. All right. So my first thought is, which one of my perfect squares, 4, 9, 16, 25, 36, goes into 12? And the answer there would be that 4 divides into 12, right? So hopefully you can just see that. If not, then you're thinking, 12 divided by 4. You're guessing and checking, right? So that'll tell you 4 times 3 is equal to 12. And again, we want a perfect square in there, which we have with 4. So I kind of split it up initially as the product or the square root of the product of 4 times 3. Okay. Now I've done the hard part. Now all I have to do is simplify. Okay. So the square root of 4 is equal to 2. So I write this as 2 times the square root of 3. Or the way you read that is 2 square roots of 3. Okay. Now, you want to kind of check a couple of things when you think you have your answer. One is, can what's under the radical be simplified? And the answer here is no. The only perfect square that goes into 3 is 1, which that goes into everything. Okay, so we're good there. The second part is 2 square roots of 3 equal to the same thing that the square root of 12 is? Okay. Well, we already did at the beginning, square root of 12 is equal to, 3.464, ... Okay. So if I type in what I think my answer is, 2 times the square root of 3, I should get the exact same decimal. Okay. And there you can see that I do. So that kind of confirms that my answer is correct. All right. So let's try a couple more, maybe a little bit quicker. All right. So in example B, I'm trying to simplify the square root of 45. All right, so a little bit of a shortcut on kind of guessing and checking what perfect squares are going to go into 45. I'm just going to look at my odd ones. So 9, 25, 49. Okay. In this case, 9 divides into 45. Okay. So 9 times 5 is equal to 45. 9 is a perfect square, so that's why I rewrote it as 9 times 5. Okay. So the square root of 9 is 3, and so my final simplified answer would be that the square root of 45 is equivalent to 3 square roots of 5. Okay, and again, we can just double check in our calculator, type it in both ways. So the square root of 45 is equal to 6 and change. 3 square roots of 5 should be equal to the exact same thing, and we can see that it is, all the way to the end of the screen there. All right, so then example C, 147 is a little bit of a larger number there. But again, we know that it's not going to be one of our even perfect squares that goes into 147. So that limits my choices. So I'm going to check, is 147 divided by 9 a whole number? 25, 49. Why don't we start with 49, since 147 is a little bit of a bigger number. So 147 divided by 49, which is a perfect square. And there you see we get a whole number. So I can break 147 in up as 49 times 3. And so when I simplify, the square root of 49 is 7. And so my final answer here would be 7 square roots of 3. 7 square roots of 3. All right, and then our last one here, 72, the square root of 72. This would be kind of a sneaky, tricky one. All right, so anyways, looking at 72 is an even number. It's a larger even number, so why don't I check to see, does 36 go into 72 first? It does twice, so there we want to say it's equivalent to the square root of 36 times 2. The square root of 36 is 6. And so my final answer is 6 square roots of 2, which is my correct answer. Now, you might have heard me mention in passing that this one is a sneaky, tough one. So here's why. And this is what you kind of have to be careful of on these. And I'll close with this. Okay. So let's say we were kind of just guessing and checking, and we said, okay, 72, I know 4 is a perfect square, so 72 divided by 4 is 18. All right, so then I could have started with, 4 times 18, and the square root of 4 is 2. So 2 square roots of 18. And 2 square roots of 18 is equivalent to 72, or sorry, the square root of 72. The problem is on this one that the square root of 18 can be reduced, right? Because, you know, which one of our perfect squares goes into 18? 9 does, right? So you would have to actually reduce this one again, okay? So you always want to try to pull out the biggest possible perfect square. So I'll go ahead and finish from how I did this one. So that would be 2 times the square root of 9 times 2. And that would be 2 times 3 times the square root of 2. And then eventually we get to the final answer of 6 square roots of 2. But you can see that it was a lot easier. We did it in a lot less steps when we took out the biggest perfect square that went into 72. Okay, so just something to look out for. So that will conclude our last set of notes in Chapter 7. After today, we start to get ready for your Chapter 7 test. Hope this helps. You guys have a nice day.